let's give it a second while my sunglasses turn transparent again. And we'll get started. Let's see, handouts. Here you go. Here are the handouts for today. Handouts. Here you go. Yep.
Thank you.
All right. Our graph's going to be on the final. So they are going to, so I think what's going to happen is, I don't think they finalized this, but I think what's going to happen is you'll be responsible for like read questions. Yeah, so you might be asked like, draw the adjacency list of this graph, or do a depth first search starting from this node and write out what happens. But you won't be asked to like, here's a graph, write code to do this or that. Yeah, because I think Wednesday will be the only graph lecture, so it's probably going to be like a read question. Okay, yeah. On Friday, you're going to cover hashing, which is also probably a read question. And then I think that's the end of the material. Okay? Hi, come on in, take a seat, and grab a handout. All right, give me 1 second while I get set up, and we'll get started, okay? Maybe take a look at the sixth graph number 6. Now, actually, let's start with graph number, let's do graph number 6, and try to trace out what happens when you do a depth first search. Okay, and then we'll get started immediately. Good morning. Graph number 6, and then try doing a depth first search starting from node A. This is odd. Okay, and then CS106B. Let's pull up code step by step. There we go. Okay. All right, let's get started. Test. All right. So, good morning, everyone. Very last section. Yay. All right, no one really cares. But yeah, so just a heads up, this class is over in like 8 days because your final exam is in 8 days. Okay? So I think it's 8:30 to 11:30 Friday of next week. Okay? And yeah, the exam is 3 hours, and I'll quickly write down the list of topics that's covered. Essentially, the key ideas are, let's see, final exam topics. Okay, so I'd say most important, which means there is for sure going to be a right question on it, is going to be something of the sort of linked list and binary trees. Okay, yeah. This is the two main questions where you're for sure going to get a challenging right question on. All right. Other ones include, let's see, kind of important. Still important are like class implementation, although. Yeah, so this likely will be a right question, but this is like more towards, essentially I'm trying to work backwards from what we've started with. So a class implementation question, possibly going to be a question, okay? Yeah, I'm not really exactly sure what's going to happen. Julie will release the final exam topics on the exams page tomorrow, so you can see exactly what the topics are. I don't think they've like exactly finalized that, but my intuition is it's going to be these two topics for sure, and then other topics which are around the weeks 5 to 6 and the last 2 weeks. Okay, as you remember, this was like week 7. This was week 8. Okay, so class implementation, that was like week 6, week 5 to 6, I guess. And then backtracking, potentially, week 5. What else? Linked lists and pointers, which I guess is week 6, was week 6.
So it will be about the same length as the midterm?
It will probably be like 1 or 2 questions longer than the midterm.
Okay.
Well, actually, the midterm was
time, right?
yeah, the midterm was 2.5 hours, I think. So maybe 1 extra question.
Okay.
It will be kind of similar in length to the midterm. Okay. Yeah. Yeah. So backtracking, class implementation, and I think the list of topics will be released here, so you'll be able to see exactly what the exam topics are. Yeah. Okay. It's not here yet, but you'll be able to see that soon. Let's see. Yeah, pointer tracing. So pointer tracing is probably going to be on the exam about how do you tell what does it mean to pass a pointer by reference and try tracing through that. Okay. Other miscellaneous topics, graphs, probably a read question because you're not going to spend any more time on graphs than yesterday. So graphs probably a weak question, and then it's week 9, I think, and then hashing. Week 9. I don't think there are any other miscellaneous topics. Sorting was not on the midterm, right? So I guess potentially sorting could be on there. All right. So this is not a fully finalized list. I'll admit I'm not too exactly sure what the exact topics are because they kind of moved the topics around this year. I'd imagine because we don't have as many topics for the final that you might get one of these two again. Right, so might be nice to brush up on those, but for sure the most important ones to study are linked lists and binary trees. Okay, cool. All right, yeah. So you're probably gonna get like a trace, definitely a trace question for both of these. So Marty and Julie, they really like to give linked list trace questions where you're given a linked list and you're saying, okay, trace through this code, what happens? Draw the end, draw the linked list at the end. Okay, it's very hard to get partial credit for those, so slow down when you do those. Make sure you get that right. Okay. Binary trees. A read question for binary trees often looks like suppose we added kind of like what we did last week. Suppose here's a list of like things to add. If we added these in order, what does that binary tree look like? You might get a heap question, heaps, which add these things to a heap, to a min heap. What does it look like? Okay. Linked list pointers. Yeah. Oh, actually, I think it lines up pretty nicely. So probably 1 read question on pointers, 1 read question on linked lists, 1 read question on binary trees, a write question for linked list and binary trees, probably a read question for graphs and maybe hashing, and then I'd guess 1 more write question. 3 to 4 write questions, so I'm not really sure where the write questions go. Okay, your tomorrow final like practice exams will be released, so you'll be able to see like what it kind of looks like. All right. Cool. So we don't have too much to cover today. It is our last section. So what I'm going to do is probably spend like 10, 15 minutes just doing a quick summary of graphs. We'll just do an example of how you might trace through graphs, just in case it appears on the final. And then we'll have time to like do 1 practice problem. I can ask for what kind of thing you want to review. So, and we can do a quick review. And then for the last 10 minutes, I'll open up to like any general questions you have. If you have any questions about future classes, about CS, about ITO NT, feel free to ask, okay? Cool. All right. Oh, and then at the very end, we're going to take a photo. Is that okay?
Sure.
Take a group selfie. Okay. I can show you my selfies for the past 9 sections. And you'll be number 10. Yeah. Cool. Okay. Let's get started. So, graphs. Let me draw this graph out, and then we'll be able to start tracing through this. Okay. Did I say number 6?
Yes.
Okay. Awesome. So 6. Let's ignore the weights on the graphs because I don't think you've done too much of with weighted graphs. So we'll just pretend that the graph just looks like this. F. Oops. G. Okay. Can someone double check? Every time I do a graph question, I always misdraw one of the arrows. Is this correct?
Looks correct.
Looks correct? Okay. Awesome. Okay. So let's try drawing what a DFS and BFS look like. Okay. What's the key idea of a DFS? Depth first search.
You exhaust one.
Mm-hmm.
You exhaust just one graph direction.
Okay, yeah. So the idea when you hear depth is you want to try to go as deep as possible. Just make choices, commit to them, and then just keep going until you reach either an answer or you've visited all the nodes, or if you reach a dead end. Okay, we can visualize what a depth first search looks like by starting doing something like this. Okay, you can actually draw what a depth first search binary tree could look like. Okay, so if we're going to turn this and we're going to trace it through like a binary tree. So suppose we started at A. Okay, where can we visit next? What choice can we make to go next? E or C, right? Okay, and then I think for this one we're going to use like alphabetical order ties. So if you have like different neighbors to visit, we'll go in the order of alphabetical order. Doesn't necessarily have to go that way, but that's often how it's implemented. So even though we have 2 choices, we're going to choose one and commit to it. We're going to forget about the other choice until later. Okay, this should remind you of backtracking, right? Where if you go down here, you can visit C. So we're going to visit C first?
Yep.
Okay, what happens after C?
Using that same logic, we go to B.
We'd go to B, okay. This is always really awkward. I should probably put this on top, put this down here. Yeah, I should probably do this. Okay, so we visited A, we visited C, visited B. Where to go next? Yeah, so we could go to A or C again, but we visited that again, so we have already marked them as visited. So now we just go down to the next one we haven't visited, F. So this goes to F. Okay, so we're here, F. What's next?
E.
E, okay. So we go to here, go down to E. All right, what happens at E?
Donezo.
We're done, right? So, well, we've reached a dead end. So what do you do when you reach a dead end? You backtrack. So we still mark these as visited, so we never visit these again. But we instead, when you trace through the program, now we're going to say, okay, we're done with E. We're going to backtrack, F. Is there another choice you can make at F? No. Okay, so we keep going back. We'll go back to B. Any other choices that make at B? No. Okay, so we go back to C. What happens at C?
G.
Yeah, you could go to D or G, right? Okay, so let's visit D first. So at C, you can go to D.
Because by our thing, if we had those 2 choices, we would go to D.
Yeah, well, we're going to use the alphabetical type breaking. Okay, so we'll get D. All right, what happens at D?
We're blocked.
We're blocked. So we backtrack, exactly. We backtrack to C, and then our last choice, we go to G.
Yep.
Okay. So let's see. We go from C, we backtrack, and we go to G. So we get something like this. Okay. Cool. All right. So yeah. Why did I draw it like that? it's because this should kind of remind you of how you do traversals in binary trees, right? The order in which we visited these nodes is the same order that we visited in that binary tree. Okay, it's just a nice representation of how we're gonna start at A. We're gonna go down as deep as possible. We're gonna keep committing to choices. Go to C, then go to B, then go to F, then go to E. That's what's called depth first search. We're going to go as deep as possible. And then when we are out of choices, we backtrack until there's another choice. Question, yes?
What if you wanted to do like A, C, G, F? Then it's already like chosen. So like, would that not be possible?
Mm-hmm. So you're saying we choose A, C, G, F?
Yeah.
Yeah, so that is possible. It depends on how you do the alphabetical type breaking. Yeah, because if you look at the pseudocode for depth first search, you'll notice there is a okay. Wait, by the way, how is depth first search usually implemented? Recursively, right? Yeah, depth first search is often implemented recursively. Why does that kind of make sense?
You need a backtrack.
Yeah, because I mean, this is kind of like a backtracking question, right? We're essentially committing choices at each step, and then when we reach a dead end, we backtrack. So that is how recursion is implemented, how backtracking is done using recursion. And then when you are doing this recursion, let's see, DFS pseudocode. Okay, you'll often see something like this, where if you reach a node and you're at a dead end, which is what often happens in backtracking, if dead end, then stop. Let me add something before. Mark as visited if dead end backtrack. Okay, so if we reach a dead end, then we just backtrack. But if we are not at a dead end, how do we get to the next node?
You see what options you have.
Okay, yeah, so you essentially go through your list of options, right? Just like in backtracking, when you have a list of options, you can run a for loop through all the options and make a choice as to which option you want to make. So for each neighbor. Okay, one important thing you want to do before you actually visit that neighbor is you do if unvisited, then recurse, or run DFS on neighbor. Okay? Yeah, this is the DFS pseudocode, right? Where whenever we reach a dead end, then we backtrack. Every step we still mark it as visited, so we never visit that node again. And then if we are not at a dead end, then we just go through all the neighbors, and if it's unvisited, then you go there and you run DFS starting from there. Okay? Cool. I want you to try one example yourself. So try running DFS on, let's do graph 1. Try running DFS starting from F. Start running DFS starting from F in graph 1. Are we done? Starting from F. Are we done?
Mm-hmm.
How are you feeling? Yeah? No? Not sure? Starting from F. Graph 1. Okay. Yeah. Could someone walk me through what the depth first search for this graph looks like? Starting from F.
Starting with A, right?
Starting with F.
Yeah, let's start with F. So yeah, you can really start anywhere, but suppose in the exam told you to start from like F.
Well, there's only one route you can traverse, so you go F
Mm-hmm.
to C to
F
B.
to C. Okay. To C. So we go start from F. We go to C.
And then you go to B,
Okay.
then E,
Okay.
and then
G.
D,
Okay.
GH.
Interesting. Huh.
And then
There's nowhere to back.
then you backtrack all the way to F, and you're like, well, can't do anything else.
Okay. Cool. Yeah. So So a depth first search would literally look like this. Okay. What do you notice about the nodes you don't visit?
There's no way to get to them.
Mm-hmm. Yeah. So one key aspect of depth first search is you will visit all the nodes that you can possibly reach. Okay. So if you were standing on F and you were thinking, "Where's everywhere I could possibly go?" Depth first search will go through every possible node you can reach. All right. If you don't, if a node does not appear in your depth first search, that means you can't visit that place. Okay. So what a depth first search is really nice for is you can often just go. It lets you find what part of the graph is connected. What part of the graph can you actually reach? All right. Let's make a more interesting example then, I guess. Let's start from A. How do you run a depth first search starting from A?
You go A to B
Okay. A to B.
to E.
E, D, G, H.
Okay. E. And then
D, G, H.
G. Okay.
D, G, H.
D, G, H.
And
Right.
then you'll
So we're here. We're saying okay, D is smaller, so we choose this one. G is next, so we choose this one. H, so we choose that one. Okay.
and then you'll backtrack to E.
Okay. Yeah.
and
So
go visit.
okay. So we're at a dead end here. So we backtrack. We go back to G. Any other choices for G? Nope. D. Any other choices for D? Nope. Any other choices for E? Yes, we can go to F, right? So E, we instead go to F,
And C.
F, and then C. And then when we're done at C, we backtrack, and we're done. Okay. Notice that we visit all the nodes except I, which makes sense because you can't reach I.
Yeah.
All right. Does that make sense? Mm-hmm. All right. Awesome. Okay. A couple things I want to mention. Let's see. Depth first search. Suppose I wanted to use depth first search to find a path to from A to G, for example. Okay. Does this find me a path of how to get from A to G?
Yes.
Yeah. How?
A.
Yeah. You can just trace from A. If you want to reach any node, you can just trace through this to get like a path. So A, B, E, D, or G. That gives you one path to G. What do you notice about this path?
It's long.
It's long, right? I mean, from here you can see there's a really obvious shorter path. Okay, so key idea is depth first search. It finds all the nodes that are connected, so reaches all reachable nodes.
So we'll find every single action out
Yeah, it reaches all. Okay, this is a bad terminology. Reaches all reachable nodes. Yeah, when you run depth first search, it will show you where are all the nodes you can reach. All right, so and then you can use this to find a path from A to anywhere to anywhere. All right, but one key feature is this path is not guaranteed to be the shortest. Okay, can anyone see why this algorithm won't give you like a shortest path?
Because like it's already marked it already marked G as visited the first time you went through the entire depth, so you couldn't backtrack to D and choose to go to G because it's already visited.
Yeah, exactly.
It only chooses one path.
Yeah, exactly. Because you are committing to choices initially, even though you don't really know what's the best choice to commit to. Suppose I wanted to find a path from A to G. I've already committed to B, and starting from there, search everywhere. Right? I did not know which one was better, but I just committed to B. So that's one reason why DFS does not find like the best. Okay. So as an alternative to DFS, there's another kind of graph algorithm. Remember what it's called?
Breadth first search.
Breadth first search. Okay. Now, just by the name breadth versus depth, what do you imagine is different?
It doesn't go all the way deep in to find every single reachable. I guess it goes and finds. It does like a top, more like
Yeah.
breadth search.
Sure. Exactly. So
Can't really describe it.
in this like tree that you're gonna draw about where you're visiting, instead of like a really deep structure where you commit to choices until you reach a dead end, we're instead gonna say, okay, here are all the choices, and I'm gonna simultaneously search through all the choices. Okay, I'm gonna focus on breadth instead of depth. Okay, so oh boy, it's this really awkward situation
Well,
where
I mean, it would also have that search, but also would have other. Never mind. Well,
yeah, okay. Let me answer that question. Give me one sec. Okay, so let's do breadth first search. Okay, so let's draw that graph again. Let's draw graph 6. All right, so let's see. One check, is this graph correct? Looks right. Okay, so suppose we're running a breadth first search instead. So we're gonna run a breadth first search starting from A, okay? How can we do that? So we're gonna start from A. The idea is you're gonna go through all your neighbors, and you're gonna like start, and you're gonna essentially say, okay, these are the candidates for where my path is going. Okay, you're gonna branch out at each step.
There's a queue.
Yes, exactly. So very importantly, there's a queue. All right, and let's simultaneously draw the queue down here. Queue. Okay, so we can simultaneously see like how the queue helped us in our depth first search. Okay, anyone remember what the first step for depth first search is, or for breadth first search?
Add it to a like the other thing that's on a queue.
Add A to the queue.
And add a to the like the it starts with an E or T. No.
There are a couple of things I
It's like you add it to like the connection or something.
Oh, okay. So you're saying like yeah. So for breadth first search, oftentimes what the goal is to find the shortest path. I'm just gonna reveal the answer. Breadth first search is often used to find the shortest path. And then to do that, it's really nice for each node if you always keep track of where your previous node was. Okay. So for example, so oftentimes you'll have this where you have a node and its previous. All right, and then I think what you're referring to is you add A to here and you're saying, oh, it does not have a previous. Okay. Okay. The first step is that we always add A to here, and then you repeat this process where you're going to dequeue from the queue. You're going to add all of the neighbors of the thing you dequeued into the queue again. You're going to mark them as visited as well. All right. So let's trace through this one more time. So we've added A to our queue. Now we dequeue A, mark that as visited, and then we add all the neighbors of A, which is what? C and E, right? Okay, so C, E. All right. What's the next step? So we're done with A. Now we add C. How do we add C?
we do the same step.
Yeah, so we do the same step here where we add C. By the way, when you added C into the queue, what you should do is you should also say, okay, C, I added C and E, and their previous was A. Okay, whenever you add something to the queue, you can also keep track of what node you came from. So we know that to go to C or E, we came from A. Okay, that's what that's keeping track of. Now we're going to say, okay, A, we're going to dequeue C, so that is going to be one of our search paths. And we're going to mark it as visited. Okay. Next step is always just add the neighbors of C.
B, D, and G.
B, D, and G. And when you do that, make sure you also add here B, D, G. They came from where?
C.
They came from C. All right? Cool. What's the next thing we dequeue?
E.
E, okay. E. So E came from A, so that's why I'm drawing it like this. And then we mark E as visited. Then we add F, right? This one. And we also specify that F came from E. All right, what's next? We're almost there.
DQ B.
B, okay. And then B came from C, so B. Mark it as visited. And then
Oh.
we add all the neighbors of B that are not we add all the neighbors of B, right? But
Oh.
yeah, but we've already added F, right?
Yeah.
We've already added F, yeah. I'm actually not super sure about the algorithm. I think I don't remember the algorithm exactly right now, but I think you should still
You should
add.
still be able to go to F.
Yeah. You still want to.
Path you haven't hit.
Yeah, you still want to add F into the algorithm. You still want to add F, but then you only up. Let's see, I don't think you add F. Let me double check which algorithm they put on the cheat sheet, just to make sure we're consistent on the lectures. This is the BFS algorithm. Here we go.
Because you wouldn't care about it, right? 'Cause
Yeah.
The other, if you go AEF,
Uh-huh.
that's a shorter way. So you wouldn't care about doing that for
Mm-hmm.
the.
Yeah, exactly. So let's see.
This one you don't care because it would be. You would have to go AB or AC BF.
Mm-hmm.
And then when you touch the other tree, you're gonna go AEF.
Yeah. Mm-hmm. Yeah. Exactly. Yeah. So for BFS, it's not super important because you'll always go in like the order. I'm just thinking. I want to be consistent with how how Julie is teaching it because usually in 106B we cover this other algorithm called Dijkstra's algorithm. It's actually a really famous algorithm. It's how Google Maps it's the basis of how Google Maps works. Essentially,
Really?
yeah. Essentially, Dijkstra's algorithm is these weights. They all have these like edges. They have different weights on them. You can imagine the weights are like distances between cities. Each of these are cities, and the weights are like distances. And then what Dijkstra's algorithm is, it finds a path of the shortest of the smallest weight. Okay, so if you imagine if all the weights here are distances, then the shortest path would be shortest in terms of the sum of the weights, rather than just the sum of like the number of hops away. Does that make sense? Yeah. Okay. So that's how Dijkstra's algorithm works. And if you're doing Dijkstra's algorithm, then that does matter about enqueuing and dequeuing which ones, but we don't really care about that right now. Okay. Cool. Dequeue from a vertex. We mark it as U, and we add each unvisited. Yeah. So here we add each of the unvisited neighbors of B, where we're going to add. Notice here that you only mark something as visited after you've dequeued it. Okay. So if we're gonna follow this algorithm exactly, we technically still add F.
So still, okay.
Okay. Yeah. Okay. But then we don't really. Yeah. This is a little awkward because technically, if you want to be consistent with how Dijkstra is like kind of more general than this, but then for this one it doesn't quite matter. Okay. All right. So let's just keep tracing. And then you go to B goes to.
But if you're trying to just find all possible, like all shortest ones,
Mm-hmm.
you would mark it not as it's in queue. So then you would never, like you wouldn't add it to like the other ACDB, ACBF. You'd only go ADF. Is that?
Yeah,
Just because.
I think
But
so.
in this one, you're gonna have 3 Fs, I guess, huh?
Yeah. Let me check. So Q is D2 is not seen, then you
With
DQ
3
of vertex
parents.
V. DQ of vertex V mark V gets visited, and then you add each unvisited neighbor. Yeah. So the idea is, let's see, we're gonna go to C, and then C we're gonna add all the neighbors of we're gonna add all of it the neighbors. Yeah. So in the end, we're gonna start DQing these, and then we're gonna do D and G, and then let's see, from A E you're gonna add F to it. If you keep tracing through this, we're gonna add D, then G, then F,
And then from B.
and then from B, well, from B we've already added F, so we don't care. Actually, I
You
think
still have to.
F is added here, right? Yeah, F is added here. Yeah, question? No?
Keep going.
Okay, any questions so far? All right, yeah, the idea is if you follow this algorithm, what you'll notice is that we're gonna keep branching at each step. And then what do you notice about this, like the depth here? So this is depth 0, 1, 2. And I think we can add one more, right? F, A, B, C, D, A, B, C, D, E, F, G. Yeah, that's 7 nodes, yeah. Okay, can you confirm, is this the breadth first search graph? Okay, what do you notice about this, like the depth? So if A is depth 0, C and E is depth 1, these are depth 2.
Well, each
Yeah.
each row down, you go all the way from left to right until you can't, and then you go down again. So you do every single.
Yeah.
You branch out as much as you can on each row
Yeah.
until you move on.
Yeah. Like how the queue works, it started at A, then it went this way, right?
Yeah.
Okay. These numbers are also significant, is because these numbers represent how far each node is away from A, right? And this does give you the shortest path. Because you are continually branching out, you're gonna consider all possibilities at each step. So because you do that at each step, you will find the shortest path. We're continually maintaining where is the next next distance farthest away we can go. So then if you keep going that way, then you'll be able to reach each one in the shortest possible way. Okay, so if you look at any path, like what's the path from A to F? Well, A to F, that's clearly the shortest path. Okay, cool. Yeah. On the exam, if you're not sure, just I think on the cheat sheet you'll find this algorithm on there. If you're not sure, just trace to the algorithm once, and you'll be fine. Okay. Yeah. Strongly suggest there are a lot of other graphs here. Try the other graphs so you can make sure that you know to do that easily on the exam. The exam they'll probably ask you to. They won't ask you to draw this. They'll instead ask you in what order are the nodes visited. In this case, for this example, what would the order be?
A, C,
A, C, E,
D, B, D, G, F.
B, D, G, F, yeah. Okay? This is the order in which you're visiting the nodes. Okay? All right. So, we're done with the material. 8. One more thing. I just want to quickly mention this thing. How is this helpful? If you wanted to find the shortest path from A to C, because your computer's not going to store it, the graph like this. So how do you rebuild where your shortest path is? Yeah. Suppose I wanted to find a path from A to F. Right? I can look at F. Where's the previous of F? E. Okay. Where's the previous of E? A. So we know that the shortest path, if you just reverse all these arrows, A, E, F. Okay, because that's why the map is helpful, because when you're actually when the code runs this, it's not keeping track of like where you came from. It's not keeping track of this tree. So we're instead going to keep track of a map of where was the previous node you came from, and then if you go backwards, you're able to reconstruct the entire path.
So would you make the node the key and the previous the value?
Yeah. Okay. Cool. Yeah. Otherwise, we're done with the material. Cool. Okay. Is there anything you want me to quickly review? I don't think we'll have time for like a full example. But are there any questions you have for the final? Something you want me to talk about?
Maybe like iterating through a binary tree. Like,
Traversing through a binary
Yeah,
tree?
yeah.
Okay. Sure. Yeah. So for binary tree traversals, remember, it's kind of like what we drew for the depth first search, where the idea is at each step you can commit to one of the two choices, right? For a traversal, oftentimes you have something like this. If you're at a leaf, or if you're at a no pointer, if at no pointer, then don't do anything. Otherwise, what you can do is you can do a call to the left sub branch. Traverse. Traverse. Okay. And what this does is it does, okay, so if you're at the null pointer, then we stop. If you're not at a null pointer, then traverse on the left side and traverse on the right side. Okay? Now, oftentimes in these traversals, you're trying to do something to each node. Right? We're trying to visit each node because we want to do something there. And then I left spaces there because you can put the code for what you want to do in three different places, corresponding to three different things you might want to do. Okay? For example, if you wanted to print everything like in order, you would put it here. Yeah, we discussed last week because everything to the left is smaller, everything to the right is larger. So it makes sense how you're going to print everything to the left first, then yourself, then everything to the right. Okay? If suppose you wanted to like free a binary tree, right? Where would you put the free?
At the point, at the base case.
I guess you could, yeah. I guess you could. If you change the base case to if we're at a leaf. If you change the base case to if we're at a leaf, then you can do that.
Otherwise, at the end of curl left and curl right.
Yeah. So, or since we're doing it at a null pointer, you can put delete cur here. Okay. Yeah. Very important. You can't delete cur here or here. Why is that?
You lose the.
Yeah. Once you delete cur, that you can't access any fields or any pointers like left or right from cur. Okay. Yeah, I saw this on some of the tiles assignments. Make sure when you call delete cur, you don't try to access cur left or cur right again. If you do want to do that, you have to keep like a temporary pointer to cur left and cur right because you can't access cur anymore after you delete it. Okay. Cool. Well, I can tell we're all bored and tired. So, any other questions?
Can you explain why breadth first search is good to find the shortest path? But why would you use depth first then?
Yeah. Depth first search that's a good question. Depth first search has a lot of applications, which unfortunately we're not going to cover. One thing is called application of depth first search is called topological sort. Topological sort, what it does is essentially it gives you an ordering of the graph so that you essentially are satisfying some sort of prerequisite structure. So, for example, if you think about what a prerequisite CS106A. Easier if I explain this using an example. 106B, and then you have CS107, CS103, CS110. Okay. Notice this is like kind of like a prereq structure, right? You have to do this before you do this before you do that. So there's an algorithm which uses depth first search that gives you an ordering that satisfies the topological ordering. So the ordering might be 106A, 106B, 103, 107, 110. Does that make sense? Yeah, depth first search can be used to create something like this because one way that you can find how deep the branches go is you can like do a depth first search. Okay, travel all the way down, and you go back up, and then you explore the other path. That lets you keep track of like where the dependencies are, and you can do like a topological ordering that way. Okay, we're not going to teach that algorithm. You're not responsible for it, but depth first search is useful a lot. Another reason why depth first search is useful because it really is how backtracking works. It really is how all the binary searches that we've done. They are all depth first searches. Okay. Cool. Any other questions? Okay. How about just any general questions you have? Considering more CS classes. Yes.
I just have a question
Sure.
with like maps.
Yeah, sure.
So when you let's say you're trying to find something, like a character in the map or something, and you want to change like the value of that key, could you just do like map, if you want to like increase that value by one, could you just do like map like key plus plus?
Yes.
Would that do it?
Mm-hmm.
Oh, that's it?
Yes.
Oh.
And what's really nice is even if key does not exist, if you write something like this, what it does is it creates the key for you.
Oh.
It automatically sets it to 0,
Okay.
and then it does plus plus.
Okay.
So oftentimes when you want to do like a frequency map, right, when trying to count how many times each element has occurred, you don't even have to check if the key is in the map. You can just say map plus plus.
You just do like
Yeah.
for block, for whatever,
Uh-huh.
and then map. Just do map key plus plus, and that's it.
Yeah, exactly.
Oh wow. Okay.
That only works for integer, right? Data.
Yeah, because if you're doing plus plus, that works for integers. Yeah, strings doesn't really make sense. But you could do something like plus equals a, or plus equals. Okay, I have no idea why you'd want to do this, but you could do this. In which case, if your key and values are strings, then what this does is it appends the value to whatever value you currently have. Okay, yeah. No idea what. I don't think this is ever a good idea, but this is one way you can do that. Okay, I can't think of a better example off the top of my head. All right. Well, if there's no other questions, can we take a photo together?
Yeah. Do it.
Okay. If you take, just especially for SCPD. Well, actually, this doesn't matter for SCPD students. Take 106L. Okay. For all the 106B students who are watching this because they didn't want to go to section, please take 106L. 106L is a cool class. It's taught by me and co-taught by me and Anna, another section leader, and then we'll be teaching it in the fall. Okay. Really chill class, and you'll learn a lot of cool stuff. We're also gonna try to bring a lot of like modern C++, that literally just came out 2 or 3 years ago, and you'll be learning really cool stuff, okay? So please take 106L. Otherwise, thanks for...
What's the gist of the class?
Yeah, just the class is you learn standard C++ that is not used, that is not taught in...
Stanford Library.
Yeah, not the Stanford Library, yeah. Remember, in industry, if you're doing any kind of project, you can't use the Stanford libraries. And one reason why we don't teach that is because there's this thing called iterators, which takes a week and a half to explain.
Okay.
And we don't want to do that in this class, but we will do it in 106L, yes. Okay? So take 106L. It's 1 unit. It's really chill. It's pass-fail. All right. Can we take a photo? Okay, and then I do want to so that this is a lecture hall, so it's nice. Come on, gather forward. Nice. This is good.
Okay.
All right, smile. All right, say your favorite topic from 106B.
Give us a countdown. Give us a countdown.
Okay, and then I always do this. Okay. Think about the worst assignment in this class and express that feeling.
Patient Q.
Okay, think about the worst assignment in this class.
The BOGO. Oh yeah.
Okay, yeah. When I said this last quarter, they were like, I don't know which one to choose. All of them? Okay, so, okay, do I see that face? Okay, and then I'll do the face when I'm trying to grade it, when I'm trying to grade that assignment.
BOGO.
All right, thank you so much. Thank you. Okay? Okay, so I'll send the photo, and then yeah, otherwise, thanks for...